Good morning, everyone from Seattle, and welcome to the fourth TSConf. Um, Here we are again online. I had hoped that we'd be able to meet in person this year. I really do miss the personal interactions that we've had that we had at our first two TSConfs. But on the other hand, it's awesome that we have these fantastic digital platforms that allow us to at least continue. And I want to give a big thanks to the SitePen team for all the work they do to pull together this conference under all of these changing circumstances. It's just awesome, and I'm really looking forward today. There's just a great lineup of speakers. It's going to be a lot of fun. And I also want to say thanks to all of you out there for all of your support of TypeScript over all this time. It really is wonderful, and we exist because of you and because of your enthusiasm. We keep going. That's really what powers our motivation. So true to tradition, this is going to be sort of a year in review of TypeScript. We're going to talk about what we do and why we do it and how we do it. We're going to talk about what's happened in our community, and then we're going to look at all of the new things that we implemented in the past year and what we're gearing up to implement, in the nearest future. I've shown this slide many times, but I still like it. This slide captures in one image why we exist. JavaScript is a language that has some issues, and we basically. But it's a super popular language, and so we see it as our job to sort of protect you from the bad parts of JavaScript and emphasize the good parts. And one of the ways you emphasize the good parts is by having great tooling. And great tooling great tooling, we all know by experience is only possible when your tooling can reason about your code, and your tooling can reason about your code only if it somehow understands what goes on in the code. And that's why TypeScript adds a static type system to JavaScript. And using then that static type system, that enables us in turn to build fantastic tooling that gives you all of the things that you want from large-scale app development, like statement completion, code navigation, and error messages, compile time validation, transpilation, and so forth. Believe it or not, TypeScript turns 9 in about 4 weeks or 3 weeks. We first shipped on October 1st in 2012. And now I have personally been working, believe it or not, on TypeScript for more than a decade, which is really crazy. You'd think it wouldn't take that long to get it right, but amazingly, we're still discovering new things. We're still paving new ground as we try to capture the semantics of JavaScript in our type system and in our tooling. I was thinking about how much time have we actually invested in this product, and I think we're now well over 200 man years into TypeScript, and it's been fun. We love doing this. We're gonna keep doing it. We keep still discovering new things that we can do as we'll see. Now on this journey, we've learned a lot. In particular, we've learned a lot about how to run development and in the open, and how to really do open source. We've now been on GitHub for more than 7 years, actually. And we've sort of boiled our operating, the way we operate down to these 6 principles, be open source and open development. We see it as our job to closely track the ECMAScript standard, but any part of the language that we share with ECMAScript, we do not see it as our job to innovate in that part. So that means the base JavaScript language, any kind of innovation that happens there, we want that to happen through TC39, and we actively participate in the JavaScript standardization process, and we've championed multiple proposals through that process. but we don't see it as our job to somehow change JavaScript outside of the normal processes. However, we do see it as our job to innovate in the islands inside JavaScript that we have carved out for our type system. And we've been doing a lot of innovation over the years, and really it's all in the name of giving us the ability to build best of breed tooling, and I hope you see that day to day when you use our product. We also are really serious about like continually lowering the barrier to entry. There's a whole sort of there's sort of a whole continuum of where you could possibly be in your usage of TypeScript. You could, for example, just use JavaScript. You could just have a project with JavaScript files, even if you open that up in an editor like VS Code that uses TypeScript as its JavaScript language service. We can still provide a whole lot of services because we can infer a lot of things even from unannotated JavaScript. And we can even check your unannotated JavaScript. Or you could go one more step and add, JS doc comments that we can then slurp up or whatever. Or you can go all the way and rename your files to .ts and introduce type annotations. And we're happy with every place in that. We see it as our job to sort of bridge that entire gap from plain JavaScript to full-on strict mode TypeScript. And of course, we're super serious about engaging with the community. I think you see that through conferences like this, but also our work on GitHub and all of our development in the open on the issue tracker and so forth. Now, it's been yet another great year for TypeScript in terms of use and adoption. In this latest Stack Overflow survey, we were the third most loved language. If you look at RedMonk's language rankings there, we are now solidly in the top 10. And in fact, it's a little bit funny too if you look at Stack Overflow survey, because they classified Node.js and SQL and HTML as programming languages. And if you remove those, really it's sort of the usual suspects ahead of us: JavaScript, Python, and Java, and then TypeScript is not. I had never thought possible, but there it is, and I think it's wonderful, of course. It's also wonderful to see the state of JS language satisfaction, where now for 4 years running, we have had the highest satisfaction ranking of any of the Java of the ECMA or target of languages that target ECMAScript. I also, a half years ago, when we were in person, which was great. And at that time, we were talking about this amazing milestone that we were about to reach on NPM of 10 million downloads per month. This month, we are close to 100 million downloads. We will, in the next few months, reach 1 billion downloads. Population downloads TypeScript every year. Rather, it's a ton of auto provision downloads from stuff. Really deep adoption that of course makes us very happy. This is our team. These wonderful people. I have still not seen any of them in person for the last 18 months, other than chance meetings on the street in Capitol Hill here. But I miss them. They do great work, and I am so fortunate to work with these people. And really skipping a beat, and it speaks a lot to that cloud workflow that we basically we're already on, because we do all of our processes on GitHub. Definitely typed, of course, continues to be a super important part of our ecosystem. Just in the past year, there were 6,000 pull requests to definitely type, which averages out to at least 25 a day. We actually devote a full-time resource on a rotating basis from our development team to continuously monitor pull requests and make sure that everything is up and running. And over the years, we've built an awful lot of tooling that powers the whole sort of definitely typed pipeline that automatically packages typings and puts them up in the @types namespace on NPM. Other tooling that automatically moves pull requests forwards, categorizes them, and makes sure that they get reviewed by the framework maintainers, et cetera, et cetera. We've done a lot of work on our website in the past year, and I'll maybe just show you that in person here. Let's go to the website, and in particular, this is just a new landing page, which is great. We've also done an enormous amount of work on our handbook. And I think in particular things that first of all, it is actually now much more up to date with the language. But also, it is now written completely in Markdown, and we run a bunch of tools as well that allows us to really create a super great experience here. For example, if you look at these examples in our documentation, when I hover over portions of the code, you'll see that I get quick info just as if I was in the TypeScript editor. This is an open source tool called 2slash that was built by Orta from our team. And we pre-process all of this documentation by running it through this tool, and then the tool uses the compiler to actually add all of these hover hints automatically. So that's another sort of great innovation, I think. If we go to the end of this page, you'll see that all of our docs are open source, and you can actually do pull requests on the documentation. And if you look at the pull requests we had in the past year, there were more than 1,200 pull requests in the year that we've had this documentation online, which is fantastic. Which means that the community is continuously making our documentation better, which is really great. I should show also another cool thing is we have now an online TSConf reference, which is really great because we have an awful lot of compiler options at this point. If you go to strict null checks here, you'll see that you can learn about all of the meanings of all of these compiler options. And that's a great resource. And of course, the playground keeps getting better. We have the ability to use multiple versions of the compiler. It's super easy to validate bug requests and build repros that you can just copy and paste into issues. And if you look at, one section that I particularly like is like the section that describes what's new in each of the versions of TypeScript, with illustrative examples here, so you can look at what is this exact optional properties. Well, here's an example that talks about what it is, and so you can see it just in terms of code, which I also think is really wonderful. Another interesting development is GitHub's web-based editor. I don't know if any of you have used it, but I would highly recommend it. Let me try and show this. It is basically the ability to fire up a development experience inside your browser directly on top of repos in GitHub. So if I, for example, go to the TypeScript repo here and I go to one of my own pull requests, here's one that I have for doing some variance computation fixes here, and let's try to look at the code in this PR. And of course, if someone wanted to review this code, well, they're looking at this browser hosted view, which is great. But it's sort of like looking through your code through a toilet paper roll, right? I mean, it's like, what if I wanted to navigate and see what does this create type reference function do? And that gets hard. But now you can fire up the GitHub web-based editor just by pressing dot anywhere. So I'm pressing the dot key here now, and you'll notice that it opens up instead of works at Microsoft. And we also have a team that's building an open source type checker for Python called Pywrite, and a language service on top of that called Pylance. And interestingly, Pywrite and Pylance are built in TypeScript, and they share. Well, they forked and used some of our code from the TypeScript type checker. So there's a lot of commonality between the two, and honestly, we're sort of in the same problem space, right? Where we are building type checkers for dynamic programming languages. So we meet with the Pywrite team every week and have a bunch of great conversations about how to make control flow analyzer better and how do we solve this problem versus how did Python solve it. So I think it makes both efforts better efforts, and I'm excited about that. And of course, I'm excited about all of the fantastic community contributions that we continue to get. We got more this year than any other year, almost 300 pull requests from 85 contributors. I've listed them all on this slide here in order of how many contributions were made, but not to, I mean, but it's wonderful. You know, we are seeing actual language features now and big ones too being implemented by the community, and we love it, and we're very grateful for that, and we urge you all to keep it going. So that's sort of a review of what's happening in the community. For the rest of the talk, I want to show you a bunch of code and demos of what we implemented in the past year. We are on a steady ship cadence now. We've been on this ship cadence for about 3 years now, where we ship 4 times a year, February, May, August, and November. And that means we have 4 releases in the past year to look at. And so I'm going to go through and pick some highlights from each of the releases and show you what that means for you in your day-to-day coding. So in TypeScript 4.1, we previewed a little bit of that last year, template literal types and recursive conditional types, but they are now fully in the product. Another feature is no unchecked index access. I'm going to take a look at those. So let's go to where my demos are at, and let's start with template literal types. So just briefly reviewing, template literal types are the ability to have string literals with holes in them, if you will, similar to template literal expressions in JavaScript. Here we declare an event name that is mumble followed by change, and when we then instantiate that type, we get foo change, bar changed, or bash change. For example, here we just get foo change, but if we instantiate it over a union type, it distributes. And if we have multiple union types, we basically form the cross product. But it's also possible to have holes that do not represent a finite number of possibilities. All of these up here were finite numbers. These are effectively infinite possibilities. So there could be any string here followed by a dash, followed by any string. And those we keep in that form, but the type checker will check that when you assign something to that type, there must be a dash. If there's no dash, you see that you get an error message. Likewise here, there has to be a dash and a number. So if this last bit here is not a number, you get an error message. Now, that's definitely pretty cool. Where it gets even cooler is that you can actually build little algorithms that manipulate types and generate new types from other types using string literal types. And so here, for example, is a little utility type called trim that trims off all the blanks off of a string literal. And you see that we do that by first inferring to something that starts with a blank and then a hole and we grab whatever is the rest there. And so if that matches, then we recurse. And likewise, we do it for trailing blanks and recurse, and then at the end we have the trim string, and you see how that works out. And with this capability, it's really now possible to algorithmically create types by operating over other types. And indeed, our type system is now it's a little functional programming language. The values in this functional programming language are types. And you write functions by implementing generic types or parametric types, if you will, where the parameters are other types. And to wit, normal functional programming language techniques such as recursion are equally applicable here. So you can write recursive algorithmic types that then compute new types by iterating. Now, that's all sort of interesting and theoretical, but now that this feature has been in use for a year, we actually have real world examples of what it looks like. And so here I'm going to show some of those. One example I stumbled across was someone giving strong typing to a nifty formatting function where you pass a format string that has named holes where values are going to go. And then you pass an object literal with properties that have those names and provide the values. And of course, in a traditional programming language, I mean, you would say format takes a string and an object, and there would be no checking here whatsoever, right? But wouldn't it be nice if we could check that this object literal you pass actually matches the names that you used here? But how would you do that? Well, you could modify the compiler and build knowledge of a particular format function into the compiler, but we don't want to do that. But now that we have computed types, you can actually write types that compute the result. And so here's a placeholders utility type that extracts a union of string literals from the names in the holes of the formatting string. So and the way this works is we infer from our string to some number of characters followed by an open curly, followed by something that we want to capture in P, followed by a close curly, followed by the rest of the string that we capture in R. And when it matches, then we say, take that P that we captured here and union it with the remaining placeholders in the rest. And when it doesn't match, then return an empty union because now there's nothing left to match, right? And sure enough, that actually allows us to infer now here that, well, you passed in name and age. Well, so we can write a format function that says S is a string, and then we can apply placeholders to that. And notice then the experience I get when I'm typing this and I press Control Space to get statement completion. We've actually extracted name, and we can just finish this off. And if I press Control Space again, now we know that the age property still remains. And also, if I misspell one of them, you'll see that we tell you this is not what we expected, right? So this is pretty cool. This is almost like a little mini DSL that you could actually implement simply using algorithmic types. Another example of that's sort of similar is routing. Like the Express framework, which is super popular, has the ability to write handlers that indeed that then capture portions of a URL in variables that you can then manipulate in your handler. And here's an example of a type that extracts all of the variable names from the static URL that you provided here, and then presents it as properties on params. So now when I say params dot, I get nice statement completion that matches what my route was. So again, super useful, something that happens in the real world, right? Similar, we have there are libraries that do things like fetch properties through dotted paths. Let's say I have a strongly typed object here that contains an array of other objects. there are utility libraries that sort of provide the ability to fetch a property by following a dotted path. And here's one example of how this can be statically typed. I'm not gonna actually go over what all of these types do, but notice you can examine that. I'll put all of the examples up in a repo afterwards. But notice how we get statement completion on all of the possible paths you could write here. And if I pick cars.0.make, you'll see that I get Ford. But if I pick cars.1.make, you'll see that I get Trabant. So another thing that happens in the real world that can now be modeled in the system. And I could go on here also. We have as clauses in map types that allows you to, for example, create, let's say you have a utility function that adds event handlers to an object by proxying it and grabbing all of its properties and then firing events when the properties change. You can model that by something like this, where now when I say Homer dot, you see that our utility type has added event handlers that are strongly typed based on the object that you passed in. So age change serves up a value that is indeed a number. Whoops. So if I do statement, you'll see that that's now a number. So again, another way that the type system has become richer. Let's take another look at one of the things that we did in 4.1, which is indexed access types. Strong. Sorry, I should rephrase that. It is the no indexed access, no unchecked index access compiler option. Look at this code and then tell me whether there's a problem here potentially. Well, as it's written currently, there probably isn't. And in TypeScript, we've always said that when you index into an array, you get the element type of the array. But technically, that isn't really safe because JavaScript has all sorts of wonky ways that you can create arrays with holes in them. Like if I try to make a hole just by not specifying an element, we do catch that because we know that that's going to produce an undefined, and an undefined was not allowed with what you said here. But what if instead I said let a equals curly curly, and then a sub 42 equals hello, and then I call foo of a. At this point, I have now created an array that has 41 holes, and then the 42nd element is present, and the length is 42. That's awfully hard for a type checker to comprehend. And so effectively, even though we could try to verify that I is less than array.length here, there still would be problems. So it really is a problem that is not solvable meaningfully in a type checker. And we've said, up until now, we've said that, hey, it is better to just say array accesses return the element type of the array, because the alternative is simply too painful. But some people want that pain and they want the stricter checking. And so now we give you a compiler option called no unchecked index access, which basically reflects the reality of the world, that whenever you fish something out of an array at a computed index, you might get undefined, because you might actually access an element that isn't there. And it is up to you now to ensure that you handle that, for example, by specifying a default value. Some people like that, and it's certainly an added level of security or type safety. But we feel that it is strict enough that it is too strict for strict mode even. You could call it pedantic mode or like stern mode or something. We haven't given this mode a name by itself, but it is an option that is not included in strict, but it is nonetheless provided should you wish to go there. So that's that guy. All right, let's try to move on to TypeScript 4.2. Which was February of this year. And some of the highlights there are that I'm going to show you is type alias preservation and leading and middle rest elements in tuples, and also some of the work we did to improve our uncalled function detection, and finally a new refactoring to implement missing helper functions. So let's go back and let's continue going here and look at type alias preservation. You'll note that I am defaulting in here to TypeScript 4.1 right now. So I'm going to show you what was the experience like before TypeScript 4.2. Here I have a discriminated union called shape, and I have a variable of type shape. And if I hover over that, yes, it shows me that the type of it is shape. But now what if I have a shape that could possibly be undefined? Now if I hover, unfortunately, we've lost the alias, we've lost the name. And now we see the structural of the type. And that's true as well down here if I intersect, or if I intersect and union, and the types get more and more complicated. Now, the thing that's interesting is that to TypeScript type checker, it doesn't actually matter because we have a structural type system. So there's no difference between shape or undefined and this mumbo jumbo here. It's the same thing to the type checker. But of course, it's a very different thing to humans, at least, because it makes it a lot harder to recognize what's going on. Let's say there's an error in my program here, for example. Now I get an error message that says type 123 is not assignable to yagity, 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 yagity. And it's sort of like you can't see the forest for the trees here. And so we did some work in 4.2 to be smarter about preserving type aliases. And I'll show you what the experience now looks like. So again, shape is a shape, but now we actually preserve what you wrote here. We preserve the name in that new union that we create, and we preserve it in intersection, and we preserve it in combinations of both. And if you make an error, it's a much nicer experience. 123 is not assignable to shape or undefined. Yes, this is actually something you can understand. There's an additional angle to this, which is the preservation of re-aliased type aliases. Say here, if we go back to 4.1, here I have a special name for array things, and then an even more special name for string array things. But when I use these type aliases, they all used to just get flattened down to the original alias. And in particular, like a thing like the omit helper type would get flattened down to pick of exclude because that is how it's written. But of course, that means that's what you see in error messages. And you go, where did these picks and excludes come from? I wrote omit. Now we do a better job of preserving these aliases. So you see T1, but T2 is now an array thing, which of course structurally it's the same. And this again is the same again, but we preserve the name. And for omit, we're also preserving the name. So just one of those things that makes life easier when you're grokking through big error messages. Another thing code rest. Sorry, jeez. Middle and ending rest elements. Again, here's the state of the world before TypeScript 4.2. You could have rest elements at the end of a tuple, but not at the beginning or in the middle of a tuple. And you will go, why? Well, why is that interesting? And we'll look at some examples of why it's interesting, but first observe that in versions later than 4.1, this is now legal syntax, and the type system actually understands it. Now, why is this interesting? Well, take an example like this. These functions, the functions exist in the real world that sort of have interesting semantics. For example, a function that takes some number of strings and then followed by a last parameter that has a different type. This could, for example, be a formatting function that takes a whole bunch of strings and then an options bag at the end that talks about how the string should be formatted, or it could be a higher order function that takes a bunch of other functions and a combinator at the end, or what have you. People write these. Now, if you were to sort of naively try to go implement it in JavaScript, you might write something like function foo, and then you might write ... strings, colon string array, and then my number as the last argument, right? But you'll quickly learn that JavaScript does not permit REST elements anywhere but as the last in the parameter list. However, you can sort of cheat using tuple types in TypeScript, and you can say, hey, my args is indeed a REST array, a REST parameter, which is an array, but tuples are arrays, and we can have more restricted types on arrays. For example, we can have an array that consists of some number of strings followed by a number. And so we can basically give a strongly typed array type to our REST argument. And of course, we still must fetch out manually the strings and the last number. But the type checker will indeed check when I make calls to this function that I am passing a compatible parameter list. Now, you could also argue maybe a type checker should be so smart that when you pick the last element out of or all but the last element out of a tuple, then maybe we should type this automatically as string array, and maybe we should type this as number. And hey, maybe this is one of those yet another area that maybe someday we'll capture in the type system. We're not currently doing that, so you do have to write an annotation here or an assertion. But still, the important thing is that callers can get strong checks. Another example here, this time using generics, is a function that curries the last argument instead of the first argument, which is traditionally how currying works. So here I have a function that takes 3 arguments, and when I curry, it curries the last argument and gives me a function that takes 2 arguments because I've provided this one, and I can keep going and say const f1 equals curry last of f2 comma 42. And now I get a function that takes 1 argument, etc., etc. And again, this is written generically here as a tuple that starts with a variable number of elements and then has an ending element. And I'll leave it to you to look over the types when you grab the examples later. I talked a little bit about how we improved our uncalled function support. Here we are again in TypeScript 4.1. And we have some code here that has an error that often happens, which is you forget to call a function. You really wanted to check whether should display returns true or false, but instead you're checking whether the function is truthy, which all functions are because they're objects. And that's probably not what you meant. And the same is true down here. And of course, you could then fix the issue by adding paren and calling the function. But there were still some issues. So first of all, we sort of had a bug that if you also check something else, this conditional, then we wouldn't warn you that you forgot to call the function, and we really should have. And down here, we now check that, yes, you call the function. However, the function returns a promise of Boolean, which is always truthy, but you probably meant to await it. So in 4.2 and actually in 4.3, they came in at different times. We now have even more cleverness. First of all, we get this particular situation correct here, and you have to call. But here, we now have a new error that says, did you perhaps forget to await here? Because we detect that you're checking the promise instead of the result of the promise, and indeed we fix the error by awaiting. So another nice thing that captures errors that often happen. Finally, let's look at a nice little refactoring that appeared in 4.2. This was actually done by the community, which is the ability to implement uncalled functions or undefined functions. So here I have a function count items that I haven't actually implemented anywhere. Now we have a refactoring that says add missing function declaration. And notice how we will we will actually infer from the call the types of the arguments to the function. So this is a nice little time saver. You can sort of program by example and then go implement afterwards. So that's some of what happened in 4.2. Moving on to 4.3. I'm going to show you here some of the interesting things. There was the ability to have separate get and set property types. The ability also to do stronger checking of overriding in derived classes. We're going to look at contextual narrowing or smarter narrowing on generic types, and finally another refactoring for import statement completion. So let's try to take a look at this. Oops. Let's start by looking at get and set typing. Here's a class that uses a private field size, as you can see, and then it has accessors that access the state that we've stored in the private field by returning this .size. But then our setter is smart, because it allows you not just to give it numbers, but anything that can be converted to a number, such as a string or a Boolean, and then it checks that it's finite and whatever, and then stores it as a number. And that really means that in real-world usage, you're of course permitted to pass a number, but you are actually also permitted to pass a string containing a number or false, for example. This happens in the real world, for example, in the DOM. There are many examples of this, and you might think then, well, then I could just model that by saying my setter takes string or number or Boolean, right? And indeed, it would now work for this, but now when I read thing.size, it reads a string or number or Boolean, and that's not what I wanted. I actually wanted to reflect the fact that when I read from it, I get numbers, but when I set it, I'm permitted to set other values as well. And now, so the new thing that we have in that we introduced in 4.3 is the ability to have separate type annotations for the getter and the setter. So here I'm saying that my setter returns numbers, but my getter permits more than that. And now indeed, when I say thing.size, I read a number, but I am permitted to assign other types. We actually have a restriction here that says you can't, for example, say that this guy returns, say, big int, because the type of a get accessor must be assignable to its set accessor. That means it is okay for you to take a broader set of types in your setter, but it is not okay for your getter to return something that you couldn't pass to the setter. Because at that point you wouldn't be able to assign a property to itself, and that sort of would be strange, right? So that's the separate read-write types on property accessors, and of course there's a corollary here that we now in declaration files support the ability to specify get and set with separate type annotations as well. Another feature we did or actually that the community did, community member did, King WL implemented this one, I believe, is an override modifier and a no implicit override compiler flag. And I'll show you by example what they do. Let's say I have a base component with some virtual methods, a show and hide component that that derived classes are intended to override. And let's say I wrongly think that the method I'm supposed to override is called show, and so I write my display logic in my derived component, and it never gets called. And I'm wondering why, and it is because I should have actually overridden show component here. We now have a modifier called override. And when you specify override, you are basically telling the compiler to please validate that I am overriding. My intent here is to override something called show. And now you'll see that we get an error message that says, oh, you're not overriding because there is no show in the base component. And of course, I could then, now that I've been alerted, I can fix it and actually override the right method. Now, let's say in the process of writing my override, I decide that I need a helper method, and I decide to call that helper method. Now I have a different problem. Now I have inadvertently overridden something that I wasn't actually even aware that the base class provided. And that could be problematic too. Now, in order to guard against that, we have a new no implicit override compiler option. And this compiler option is one you can turn on if you want to. It is not part of strict, and I'll explain why. But you'll see that at this point here, it says you need to say override because you're overriding here, and you didn't say it. And that, of course, can then, I could even now choose to override, or I could give my helper method a different name that doesn't conflict. And you might ask, gosh, this is super useful. Why didn't you just enable this by default? Well, because there's an awful lot of code out there that looks like this, right? Where, yes, I override, but I didn't say my intent because we didn't make you say the intent previously. So this new flag basically makes you say the intent, but it is a breaking change to turn it on. Meanwhile, it's maybe a breaking change that you want, but that should be your choice. So this is a safeguard that you can turn on or off if depending on how much validation you want. Let's look at some improvements we did to control flow analysis of generic types. This is actually, if we go back and look at this issue we have here, try to click on it. There. This issue goes back, more than 4 years. And someone was complaining here, and I'll show you what the issue is. Let's say I have a generic function that takes a t, and my t is constrained to string or undefined. And then I check whether my x is undefined. And now you wonder what now inside this guarded block is the type of x. Well, surely x is still a t. I ought to be able to assign x to something else of type t. But it is also a string, yet t could be string or undefined. So it's really sort of like, it's like a t where the constraint has changed to just be string, but that's hard to model because that would need a new type parameter or whatever. So traditionally we had some issues with this where we would say, we don't narrow generics because generics are themselves not union types. But they might have union type constraints that we would like to narrow. And then we would do that in certain cases where we're absolutely sure that that's a fine thing to do. Say you say x dot length, for example. Here, well, we know that we're going to be accessing the constraint of x. So why don't we start by narrowing x to string or undefined, and then we can narrow away the undefined by observing that there's a guard, and then you can actually access length here because syntactically we know that that's a fine thing to do. But we would error here, for example, where you call take string with an x, even though it indicates that it just wants something that isn't a t. And here in the return, we're returning a string. And so there's an indication that we shouldn't really care about the t-ness anymore. And so that's what we've implemented in 4.3 is what we call contextual narrowing of generic types, where we observe that, hey, x in this particular case here is used in a context that doesn't care about its generic type. And so we can safely narrow it and then get further narrowings from control flow analysis. So here we actually narrow x first to string or undefined, and then control flow analysis narrows it to just string. But here we know that we're in a context that cares about generics because we're assigning it to something that's of type t. So we don't narrow here. So it's sort of like you can have your cake and eat it too solution to the problem. But it's nice to finally. It took us 4 years to think of this, but we got there. Um, Let's look at another cool little feature that was in 4.3, which is import statement completion. Here I have a project that I'm using Node, so I've installed the typings for Node in my Node modules, and now when I say import and I start typing, you'll see that we get statement completion on all of the things I can import from the modules that are part of my project. And we do that also by looking at your package.json and what have you. So I can simply statement complete by pressing tab here, and we'll write the rest of the import statement for you, including which module you imported from. And so now, of course, if you then try to statement complete, now you only see things that come from FS, right? Like watch file. And I can grab more from there. And I say I could import log from console. Just makes it easier to write these imports that we all have to write. It is funny, by the way, how in Python you first say what you're importing from, and then you say what you're importing, and and that's actually also the case like in Link and C# and other things that look like this, where because from a statement completion perspective, we don't know. We have to look at the entire universe, to begin with, because you haven't told us where it's supposed to come from. But I think this is a pretty clever solution to that issue. All right, whoops, and that brings us to 4.4, which we just shipped in August. Okay, we're good on time here. And some cool things ended up going in there, like in particular, like control flow on constant conditions and index signatures for more types. And then we have a couple of new interesting compiler options that we'll also try to take a look at. So let's start with our improvements to control flow analysis. This again is super old issue. Let's try to go back in time here. From 2016, someone was complaining that I can't narrow based on a computed Boolean condition here. I am forced to write the condition inline every time. And it's something that we've chewed on for a long time, and I think we had imagined some very complicated solutions to this issue, and then it turns out that it wasn't actually that hard to fix. But let's just first observe the state of the world before 4.4. Here I have a piece of code that narrows my argument based on the check that it's a string, and so in here arg ends up having type string. Let's say that I refactor here and I extract this to something like, say, arg is string, a Boolean that computes the same thing. And now the narrowing goes away because we look at arg as string and we go, well, that's just a Boolean, and so that doesn't do anything for arg. Well, it turns out it does, but we're not seeing that, so to speak, in the control flow analyzer. But our vision has gotten better in 4.4, and we now actually grok this. And we understand that arg is string indeed is really just an alias for this condition. And what our control flow analyzer does is, in certain circumstances, I'll talk about what those are, in certain circumstances, it will then inline. It'll really sort of treat arg string as a macro and inline it right here and pretend that you had said type of arg string right here, and then indeed you do get the narrowing. So let me talk about a little bit about what are some of the limitations well, first of all, the computation that you do, the capturing of the Boolean condition has to be stored in a non-mutable local. So if I said let arg is string here, you'll see that we do not narrow because there might have been in the intervening space right here some assignment to arg is string that we don't track. Now, of course, we could do that work, but that would be even more work for the control flow analyzer, which means it would go slower for all code out there. And so it's always a balancing act that we're doing there. And so we're saying, typically the right thing to do anyway is capture this in a const. And so we simply just check that if you are trying to check a condition that was stored in a const, then we will look at that condition in situ. Now, we also require that the thing you check in the condition itself is const. Now, I didn't actually say const on my argument here, but we do treat arguments that have no assignments in the function body as the same as const. So if there was an assignment in the function body somewhere, you'll see that, again, we don't narrow, because that assignment might have happened intervening in between the test and the time that you are checking the test. Again, we could do more work in the control flow analyzer to see if there are any intervening assignments between here and the place where you computed the conditional. We don't currently do that work because, again, it would slow everything down to do it, and it's really not a typical pattern anyway. So that's the simple narrowing. We also do the same for discriminated unions here. So I could extract a discriminated union check into an is circle local, and you'll see that the code continues to work. We narrow shape here to a circle, and here we narrow it to a square. Indeed, you can actually extract just the discriminant itself. Let's say instead of extracting the entire condition, I extract just shape.kind into a local called kind, which is another pattern that's quite common. Let's say you're going to check your discriminant multiple times in your function body, so you put it in a local because that's more efficient than accessing properties. And previously we wouldn't be able to get that. Now we do. You can even use a destructuring to capture it, so because we consider those to be the same, and that again is a common pattern. There's another common pattern that we're currently not handling, which is where you use a destructuring to extract both the discriminant and a payload that is present in all discriminants, in all variants, but has a varying type. And you extract both into locals. And now you sort of have these two appearingly disconnected locals that actually are connected. The control flow analyzer does not have the ability to see that currently. It's something we're still thinking about. We might be able to get that, but that was not in this work. Finally, this composes nicely too. Let's say I have a string or number or Boolean, and I compute, whether it's a string and whether it's a number and whether it's a string or number, and we actually get that as well. Here it's string or number, and in the other branch it's Boolean, which is lovely. There is some limit to the amount of nesting. I can reveal that it's 5. I've never seen any code that went deeper than 5 levels of nested checks, and so our analyzer just says after 5 levels, stop inlining. Yeah, so that's control flow analysis. I think that's a really super nice problem to finally have solved. Another one is index signatures, or some of the restrictions that we have traditionally had on index signatures. If we go back to version 4.3 and earlier, if I try to write an index signature for symbols, for example, which is something that people have wanted to do, I would get the error message that, has to be a string or a number, nothing else is supported. And that was traditionally the way that we represented index signatures. But as JavaScript has grown more advanced and as our type checker has grown more advanced, there are some very common patterns that you could not capture with these restrictions. And so in 4.4, we're lifting the restrictions, but with some caveats that I'll talk about. It's now possible to declare, first of all, an index signature for symbol. And when you do, then you can index with symbols, but you cannot index with strings or other things. You will get an error on that, and that's lovely. Now, the restriction on index signatures now is they can effectively be any type you want, but the type must be something that could not be represented as unit types or literal types. It must, in other words, be something that represents an infinite set of possible values, or almost infinite. So let's say I try to write a key which is either quote A or quote B. Well, that I could have written as two properties, optional properties called A and B. So index signatures are not the right thing to use to implement that. So, but if I use a type like symbol or string or number or some type that represents an infinite set of possible values, then an index signature is the correct construct, and then we do permit it. Let's look at another example here, which is template literal index signatures. Let's say I have an options bag that has a width and a height that must be numbers. And then, by the way, my options bags allows me to have properties named data mumble of any type. And I can have anything I want as long as it starts with data mumble. That's now possible. You'll see that this thing represents effectively an infinite set of possible values. It's not something that could have been represented by a finite set of declared properties. And therefore, we permit it as an index signature. And we check it accordingly. So here, you can have a data foo, but you cannot have a bad foo because that does not meet this pattern. That actually is pretty common even in HTML, right? To have data dash properties and so forth. So now you can actually model it. Another problem that this solves is a long-standing request for the ability to have index signatures for tagged primitive types. It's common in TypeScript to use this pattern of I'm going to take a primitive, I'm going to have special kinds of strings like product IDs or social security numbers or phone numbers or what have you that have been subjected to some validation, and that validation is indicated by the attachment of a tag. And so you can't just assign a normal string to it. You must first validate it, and then you get like an ID string, for example. And this is the pattern that people use. But of course, you also want the ability to have index signatures for these things, so you can have dictionaries that can only be indexed by IDs, for example. And that now becomes possible. So here I have a regular string and I have an ID string, and I have a dictionary from ID to string. I wrote it as record of ID, comma string. You could have equally well have written it as just an index signature for key colon ID. It's the same thing. And you'll note that I can't index with a plain string, but I can index with an ID string. Finally, another long-standing request is why can't I write a union of possible things in my index signature? Well, previously, you could only have written string or number, but why couldn't I write that? Well, now you can. Again, of course, each member of the union must represent an infinite set of possible values. You can't have literal types here, but you can combine like template literals with placeholders. You can combine tagged literal types or tagged primitive types and so forth. And we basically just flatten that out to a set of index signatures for each of the types that you mentioned in the union. So that is that work, and that is in 4.4. Let me also show another interesting feature. Actually, this sort of goes back to all the way at the beginning of TypeScript and the way that we have traditionally treated try catch and specifically the way we type the catch variable. When you write a type catch, ever since day one, TypeScript has simply given type any to catch variables, which Back in the old days was really the right thing to do because any was our top type and it was our only top type, and we don't know what E might be here, so we gave it type any. But of course that meant that you could write anything you wanted. You could access any old property you care to here and never hear about it. And even then, you might actually also hear there's no guarantee that the thing gets thrown will have a message property at all. You might throw 42, you might throw something that isn't an error object, right? And JavaScript is perfectly happy to do that. It's unfortunate, but that's the reality. Now, a few versions back, we allowed you to at least put an annotation here that treats it as unknown, which is in today's world, that's what we would have done. We would have said, we don't know anything about this E, so its type is unknown, which is the safe top type, if you will, right? And here, then you would have gotten an error, or you will get an error. But now, of course, you have to remember yourself to write these type annotations every time, and that's cumbersome. So in TypeScript 4.4, we have now in strict mode included a new compiler flag called use unknown in catch variables. And so when you're in strict mode, your catch variables now get type unknown. You can, of course, do the opposite and give them type any if you want. That's fine. But you have to manually say. So we don't have like that implicit any that came out of nowhere that we used to have. And that's definitely the intent of strict mode. So I think this is a nice thing. It's been long overdue. It would be lovely if we could know more about E here, but you can never be quite certain. So some people have suggested, oh, we should just give it type error because that's what it always is, or almost always is. Yes, well, sorta, kinda, but there's, as you can tell here, it's very easy to make a mistake, and now you have a bug in your program that you never heard of. So that's that one. And final thing I wanted to show from 4.4 is a new compiler flag called exact optional properties. Again, let me just start by showing you the history of this one. This goes back to 2016, yeah, 5 years ago. Someone pointed out, and look at all the upvotes, that our treatment of optional properties is kind of wonky, and I will agree that it is, and I'll show you what the wonkiness is. This is the state of the world as it exists without this new compiler option. Now, I should preface it by saying, as you all know, in JavaScript, JavaScript permits you to read properties from an object that don't exist, or properties that don't exist, and you just get undefined. And that's been a built-in behavior since day one. Some programming languages don't. They were giving you an error, but that's not JavaScript. So in JavaScript, when properties are optional, you simply read an undefined. But there's a distinction there. The undefined that you get back, did that mean that the property wasn't there, or was it because the property was there and had the value undefined? For most cases, you don't really care. I mean, I knew I just got an undefined, but the distinction really that between the two is, should you permit it to assign undefined to an optional property? And that was a distinction that traditionally we couldn't make. When you wrote A question colon string and B question colon string or undefined, well, we treated A question colon string the same as if you had written string or undefined, which means you said, hey, a possible value of my property is undefined, and therefore we allowed you to assign undefined to the property, which would make the property exist and have the value undefined, which is not what you had intended, really, because you had just said string. So you sort of see the dilemma there. And it's something that rarely matters, but it does matter sometimes, in particular when you're like doing object spreads and you are dealing with optional properties in React, for example, and other frameworks. And so we now have a new compiler option that I'm going to turn on called exact optional property types that you could argue does it now the way that if we were to do it over today, this is how we would do it. Now I'll talk to you about why we can't make it the default, but observe what happens now with this option on. If I declare obj, we now make a distinction between whether you set string or whether you set string or undefined in the type annotation. The first one means if you assign to it, you must assign a string. But of course, when you read from it, you might get undefined because it might not be there. Whereas B says you can assign string or undefined to it. And of course, when you read from it, you might get undefined, and you can't tell whether it was because the property wasn't there or because it was there and had the value undefined. And now notice how this is an error. You cannot assign undefined because A says only thing you can assign is strings. Now, with that in place, it turns out that now we can give safe treatment to the in operator. When you check whether here, when you say obj.a.length, well, you can't do that because A might not be there. But if you check that A is there, then indeed we can narrow safely the type of A to string versus string or undefined up here. And the same if you call the hasOwn property method on object, then we will actually narrow. We could not do that narrowing before because we would not know whether the property was missing or whether it was there with the value undefined. Now, an interesting effect of this is that for optional properties that don't include undefined, you can't just read them and assign them to themselves. Here, if you say obj.a equals obj.a, that is not permitted. And you can sort of go, well, it kind of makes sense that it's not permitted, right? Because if I were to read here and A wasn't there, I would get undefined. And then I would stuff undefined into A, which is exactly the thing that we want to avoid. So in order to assign a property to itself, you have to first check that it exists. And then we will permit it. Now, as I said, in a green field, in a new world, this is how we would have done it in the type checker. But it is a breaking change to do it. And the reason it's breaking is that there is like an enormous, like you could argue this should have been part of strict mode, right? Shouldn't it? And we had it as part of strict mode to begin with. But it breaks a lot of stuff. In particular, on definitely typed, there's gazillions of typings that are written without regard to whether the library actually permits you to stuff undefined into properties or not. It's very typical to write this, but really mean this, because it's shorter to just write string, and we know that the compiler is going to slap undefined on it anyway, so why should we write or undefined? But making that distinction causes a lot of the typings to become too strict on definitely typed. And so we looked at that and we go, okay, this is too breaky to make it at the default. So we did not make it the default. We are doing work currently to get definitely typed into a correct state where all of the declarations of properties actually say what the intent is. But I'll be honest, it's hard to know in a lot of cases what the framework actually does. Does it actually make a distinction between properties that don't exist or properties that have undefined values? It's sadly not very well documented by most frameworks, so it's not clear that we'll ever be able to go there with strict mode. Anyway, that's what happened in 4.4, and that sort of takes me to a quick little preview of what we're looking at for TypeScript 4.5. One of the important work streams is that will hopefully come to fruition in 4.5 is support for ECMAScript modules, native support for ECMAScript modules in Node, the ability to have MJS files and all of the other interesting extensions that Node will support, and 2 node resolution modes, either common JS resolution or ECMAScript resolution. That work we hope to land in 4.5. I'll show you work that has already landed and is in the nightly, tail recursive conditional types. And then another piece of work that I think is going to be lovely is the ability to have your library d.ts files as npm modules, so that you can basically bind yourself to a particular version of, say, the DOM, as opposed to always get an updated version that comes along with TypeScript. And some other work. If you want to look at our iteration plan, you can look at this issue here that outlines what we're doing for 4.5. I wanted to preview this tail recursive conditional type work because I think it's interesting. So let's try to just let's try to fire up a little example here. And this one shows you the state of the world today. And so earlier when I was demoing this little trim utility type, I was carefully avoiding a bit of a landmine that exists in today's compiler, which is our type instantiation recursion limiter. Now the TypeScript's type system is Turing complete. It means that you can write non-terminating algorithms in your types. You can, for example, make a mistake in your trim function here, or trim that just infers the same type and then recurses forever, and the type will never stop recursing. And so we have to have something internally that limits this runaway recursion. Because if we don't, then we blow the call stack, because the compiler internally uses recursion to evaluate recursive types. And so we've had a limit of 50 levels of nesting of generic type instantiations. And once we reach that limit, we basically say, this is not going well, this type is excessively deep and possibly infinite. And that's the error message that you see here. But it is kind of silly. I mean, obviously, you can have strings that are longer than 50 characters, right? And that's what this is an example of. So we thought long and hard about that. We tried for a little while in the nightlies for 4.5. We had we tried to increase the nesting level to 500 levels and then we started seeing stack overflows in certain browser environments, because while Node might have a fairly large allowance for call stack, a lot of browsers don't. And so, and sadly, like when you blow the call stack in a browser, often the browser just stops running your program, and it doesn't even tell you about it unless you're in debug mode. And so that was a very bad experience. And then we sort of went back and we go, well, but this is a known problem in functional programming languages. And functional programming languages have this nifty little trick they call tail recursion, which is when a function ends by a recursive call to itself, then it can be turned into a loop through an optimization, right? Instead of having the last instruction in the function be a call to itself and then immediately followed by a return, you can, in a sense, just change it to a jump to itself, which is a loop, right? And it turns out we could do the same trick in the type resolution logic in the compiler, and that's what we've chosen to implement in 4.5. And so I'll show you what that looks like. So if I move to 4.5 now, indeed, we can have, string literals that are effectively arbitrarily long. I could just keep on going. But of course, we still have the problem of non-terminating types. So there has to be some limit. So now we have another limit that says after 1,000 iterations in a loop, evaluating a tail recursive type, we will stop and say this is not going well. But we think that is a much more practical upper limit, and I don't think that anyone will run into that. And if they do, quite honestly, then maybe maybe they should not be programming in the type system. Maybe they should be programming in an actual programming language. Here's another example. The reason this worked is that we did add a little more space to the default limit of recursion, where we say we now allow 100 levels, which by experimentation looks to be just fine in all browsers. But so this type here that extracts all the possible characters of a string in a union type, like there. If I double the lengths, we will still error because this type here is not tail recursive. It ends in recursion, but it recurses through a union type. So there's not a direct invocation or a direct reference to getChaos itself. But it's possible, actually, and fairly easy to rewrite this to be tail recursive. And with a little trick where you introduce an accumulator. So I'll show you what that looks like. I'll introduce an accumulator that I default to never. And then whenever I succeed in matching the patterns, I invoke getChaos on the rest, and then I pass char union with what I have accumulated so far as my accumulated result. And then finally, when I'm done, I just return my accumulated result. This is now tail recursive. You see that it references itself. And that means that we will loop. And that means that now you can have arbitrarily long, up to 1,000 character strings here. And actually, not only that, evaluation is also more efficient because we're not like building up a big call stack. So that's tail recursive types. And you can look at the pull request if you want more details on that one. And that sort of brings me to the end of what I wanted to demo. I wanted to just, wrap up. Let's see, we still have, we probably have time for a few questions here. But let me first wrap up with a plea to you of some things that I think would be great if I could help you do when you use TypeScript. First thing is, please use strict mode when you write code in TypeScript. Strict mode is not the default because making strict mode the default would break a lot of code that doesn't use strict mode. But strict mode is the mode that we reason about daily when we implement the type checker. And quite honestly, non-strict mode is, the semantics are getting more and more fuzzy of what really is being checked here, and so we would urge all of you to please default to strict mode in your projects and endeavor to move your existing projects into strict mode. And of course, you can then opt out of certain checks if you so desire, but strict mode is really where you want to be at. I would also be super happy if everyone would try the nightly builds, because when people use the nightly builds, we hear about issues in new features that we're implementing much sooner, and they are much easier to fix because we can fix them before beta or in beta or whatever, as opposed to after the space shuttle flies, so to speak. So give the nightlies a whirl. We endeavor very hard to make the nightlies very stable. We run like huge test suites on them before we publish them. And we've made it super easy in VS Code to just pick a different TypeScript. So please give it a shot, at least in your editor, use the nightlies. Please vote on suggestions on the GitHub issue tracker. As you saw, some of these long-standing issues, we don't forget about them. We keep thinking about them. And the more upvoted they get, the more we think about them. And ultimately, that comes to fruition, and we figure it out and get it implemented. I would urge you listening today, in particular, to please help out on Stack Overflow and on Discord. You guys are the brain trust of TypeScript, and any help you can provide there for the community, it makes the world better for all of us. And finally, we love all the work that our contributors are doing. Like I said, this year was the biggest year for community contributions, and I can't welcome them enough. Please keep it up, and please dive in if you're so inclined. So that's it for my talk. I think we have about 10 minutes for questions. Daniel's been texting me here, so let me see what some of them are. Regarding type checking the catch variable, should there be a throws error type annotation similar to return types? That way you could type the catch variable based on what you call. Yes, that would be lovely, and it's something that we still think about. But unfortunately, it's a transitive problem of well, what is what you call, and what does that in turn call, and how do you really know what you call is like without annotations on what that calls, it becomes hard. You could make them into assertions where you're just sort of blankly asserting this only throws errors, and that might be where we land in the end, where it is sort of based on you simply saying, I don't care, just pretend that no bad exceptions ever come out of this. But there are certain kinds of exceptions in JavaScript, like the Stack Overflow exception. That could happen at any point in time, and then so it's always like, I mean, because people also want this to check that no exceptions are thrown, right? And even that is hard. So it's hard to do this. And I think where we're at now, we can at least safely say that we're not trading one problem for another. We are actually now in strict mode, truly guarding you against issues. Of course, then in your catch clauses, you can write some instance of checks that then checks that your exception is what you expect it to be, and otherwise does something else. And now you've actually written code that is provably safe. But we haven't forgotten about this issue. It irritates us as well, and so we do keep thinking about it. Trust me on that. Is there a world where strict mode has something similar to Rust's editions, where different editions of strict mode have different defaults? Well, I think we sort of have the view that there are two worldviews you can have. You're either not in strict mode or you are in strict mode. When you're not in strict mode, nothing is supposed to change between releases of the compiler, in a sense. All the defaults are going to be the same. And so you, in a sense, starting with a baseline, and then you can opt in to compiler options explicitly by saying strict null checks and strict function types and strict this or that or the other, strict optional property checks and what have you. Or you can be in strict mode, which basically says you get everything. You get all of the new strict checks, and then you can opt out of them. But you can at least give it a try. See if you build. Hey, if it built with that, great. Now I'm further protected, right? If it didn't, well, then let me figure out which of these new compiler options do I need to opt out of in order to get my code back to compiling. And then I can, like, on my own time later, re-enable it. And that's sort of that's the worldview that we really want to have, is that strict mode is the default, so that you at least get to try it, and then you can easily opt out, because we put all of these new things that we do under discrete flags that we then just group into strict, right? But you can always opt out of them. Let's see. Another question. Is there a way of progressively enabling strict checks on a per file basis? Not currently, no. And it's not easy to do, because it gets a little wishy-washy where, like when you're checking syntax and grammar, clearly there's affinity to a single file, right? I mean, like this syntax error occurred here in this file. But when you're checking semantic errors, where did the error really occur? If you're instantiating in one file a generic type that came from another file, and that file said don't check, and your file says do check, what do we check? So types are ephemeral, if you will. They're not affinitized to a particular file. So it's very hard to design a mode that is file oriented for strict mode, and that's why we don't do that. There are certain things that certain checks that are more closely affinitized to the location of the code, but it very quickly washes out. So that's why we don't. Okay, I am pretty much. My God, I actually managed to finish a talk before time. I have 3 minutes left. I think I'm. What's that? Sorry. Um, yeah. So I think I'm gonna call it here and actually bank the 3 minutes for my for my next TypeScript keynote. We will be in person. So I want to thank you all for being here, and I really look forward to the rest of the day and look forward to engaging with you more on the issue tracker and all the other media, and hopefully in person sometime soon. Thank you. Thank you very much.